Hello everyone, and welcome to my talk on reducing the sensitivity of quantum gates to laser intensity noise, but in general to any kind of noise, via real-time feedback on gate parameters. I'm Ramon Smook, I'm product manager for AMO QPUs at Quantum Machines, and I'll be diving in. So the basic idea of the quantum orchestration platform provided by Quantum Machines is to allow you to run even the most advanced quantum algorithms out of the box from a super intuitive programming language. So the basic idea is that we have devices which contains inputs and outputs, DACs and ADCs, and digital outputs and digital inputs, analog and outputs and inputs, and they are all controlled from one FPGA per box per device. And this FPGA is programmed via our own programming language, which we call QUA, which you can see here. And the programming language, this programming language is then compiled to our own assembly low level, which then executes on the FPGA. The idea is that this programming language is very high level, embedded within Python, and allows the generation of pulses and the analysis of pulses in real time. So for example, the waveforms are not stored necessarily as they would be in an AWG. Only envelope information is stored in memory. So if you would want to play a Gaussian waveform, for example, a Gaussian envelope with a 100 megahertz carrier, for example, you do not need to provide the samples for the 100 megahertz frequency component. You only provide the samples for the envelope, and the frequency component, the frequency content itself, is generated on the fly by the pulse processor. You can also manipulate amplitude and duration of pulses in real time, and then we will perform third order Lagrange interpolation in real time. You can scale pulses, you can stretch pulses, you can do real-time decision making. So we have for loops, so if then, switch case, while, everything you would expect to see in a high-level programming language such as Python, for example, but this time everything is compiled to a strict timing FPGA executed code that runs with minimal latency. Every operation in QUA has a deterministic amount of time, a strict amount of time that it takes to execute. And so you can program basically real-time sequences with decision making from a very easy and accessible programming language, and giving you a lot of performance for very little hassle compared to programming your own FPGAs or any other alternative. We will see in a moment some details of QUA and the quantum orchestration platform in general, but in 12 minutes we won't be able to cover much. So I invite you really to come to our booth and have a live demo. We could spend half an hour going over the features that you care most about and go deep. This is just kind of a taste of what we can do in the context of generating driving pulses for qubits. So let's start with maybe the most simple example that we have for real-time parameter stabilization with the QOP, and that's just a simple PID on gates. So this is, let's say, stabilization, or a toy example of stabilization of gates, gate to gate. So this is like intra-circuit gate stabilization. And let's imagine that these Gaussian wave packets are your gates that you apply consequently. And so what we do here is that we put like a photodiode on the path of this laser beam. We acquire this Gaussian as it's being sent to the qubits, to the atoms or ions. We then perform an integral in real time of this Gaussian, and then apply a PID kind of circuit code to stabilize the integral under the curve here for the Gaussian. So basically stabilizing the phase rotation applied on a qubit. And so gate to gate, we're running a PID on the integral of this Gaussian. And so you see the integral, the error of this integral here. You define some set point. I will show you the code in a moment. And so this stabilizes gate to gate, not shot to shot. So the latency involved in calculating the integral and calculating all the proportional, integral, and differential signals is what you see here. It's about, in this example, it's about 380 nanoseconds or so. So latency we count from the last acquired sample to the first played sample, right? And so 380 nanoseconds or so of latency is translated into about 300 kilohertz of lock bandwidth. The cool thing here is that this PID is now living inside QUA, so you can intra-shot, intra-gate decide which kind of set point you want to apply, whether you want to apply the feedback at all. You can do decision making within the PID and within the circuit. And so it's very robust. It's more robust. It's more versatile than just applying an analog PID, which, by the way, has its advantages, higher bandwidth typically, but it's typically not kind of coherent with the operations happening within a shot, right? It's very hard to synchronize external PID, drivers on a nanosecond time scale intra-shot. Okay, so this is the simple example where I stabilize the intensity of these Gaussian gates. If I now apply, so this is the code, sorry, this is, so just to show you basically the takeaway message is that you write something that looks like Python. We are actually writing this within your Python IDE, so QUA is hosted by Python. So this everything below this with program as adaptive gates is QUA, anything above is Python. So with 5 lines of Python and 15 lines of QUA, which reads off like PID pseudocode. Basically, you measure some, you send some pulse, some Gaussian pulse scaled by some amplitude to your laser, you integrate it, and the result of this integration with some integration weights is stored into a QUA variable that is called integ. And then you assign an error and an integrator error and a derivative error, and then you calculate the new amplitude, and you do this in a loop for 10,000 shots or whatever, and this stabilizes at 300 kilohertz or so. So this is very simple code compared to what you're getting, and you're building your own control feedback. Basically, you're not limited by some PID IPG block that you're getting from some other vendor. This is you as the user writing it. It's so simple that it's there's no point in wrapping it. So just some performance. So if I introduce a 50 kilohertz sideband here and I turn the lock here, so every point in this graph is an integral of a Gaussian, right? It's an integral of this 100 nanosecond gate. I apply some 50 kilohertz modulation and I start the lock here. I drop it to the noise floor basically of my detection. And here this spike is where I stop the noise, just to show you that locking is bringing it back to the detection limit, which isn't that good here. So I'm not trying to say that this is a toy example. And you can also optimize PID parameters on the fly because everything is done in real time. At 200 kilohertz, you're removing everything. As I said, the bandwidth is about 300 kilohertz. At 300 kilohertz, what I mean is that you have zero gain basically on the feedback. So at 200 kilohertz, you win about 10 dB on the noise power spectral density. So it's not perfect, but you still, you wrote 15 lines of code and got 10 dB at 200 kilohertz. That's quite nice. So this is the basic use case for a basic toy example for stabilizing gate. But now, and of course, then you can, clients of us have done Bayesian estimators, machine learning models running in real time in QUA, right? Because it's a very simple language to work with, and then and it's very flexible and allows you to do everything you would be able to do in Python, but with strict timing and in real time. a new feature that is coming out in the next few weeks is the ability to do what we call piecewise linear driving fields. So this is an example of an atom arrangement waveform where I'm taking, so this is a spectrogram, it's not a time domain image. So we have a pulse here that is about 200 microseconds, and every waveform here, so these are 18 tones that are driving qubits, driving atoms in an atom arrangement sequence in a minimal jerk trajectory, but this is not the point I want to convey. What I want to convey is that the way that we generate these waveforms, since they are analytical, is that we break them into piecewise linear segments. Every piece here is 300 nanosecond in this example. Why 300 nanosecond? Because these tones, these frequency chirps, they follow a fourth order polynomial, okay? And it turns out that in QUA, to evaluate this particular fourth order polynomial takes about 300 nanoseconds. And so if we split these waveforms into segments that are 300 nanosecond long, we will be able to calculate the polynomial, the waveform, as it's playing. So we will start by playing one segment, by pre-calculating the first 300 nanoseconds, which take 300 nanoseconds, and then play it. And while the waveform is playing, calculate the subsequent segment. And so if the waveform would be more complicated, you might need to use segment sizes that are longer to avoid having dead time. But this also allows you to introduce frequency modulation, amplitude modulation, calculated on the fly, but also interlacing measurements. So you could, for example, have a waveform that is 100 microsecond or 1 millisecond long, having some AM FM trajectory that is defined analytically by some function that we can evaluate in real time. And we have a very extensive math library that allows you to calculate trigonometric function, logarithms, exponents, and so on, but also interlace measurements. So you could, for example, measure the intensity of a laser, beat your laser against a reference laser, and demodulate the relative phase and extract that as a parameter within, let's say, a microsecond. So you could say you can do segments of 500 nanoseconds or 1 microsecond, and you could feed back on the gate as it's playing segment to segment. So you could have a 1 millisecond pulse split into 1001 microsecond segments or 2500 nanosecond segments, and every segment you can perform a measurement and feed forward the result of this measurement to the next segment to stabilize the overall gate against laser intensity fluctuation, phase noise, maybe up to a certain bandwidth, and so on, magnetic field instabilities. And so this is a cool new feature that you can do. And I invite you to the demo to the booth to see a demo, because this is a bit too details to go over in 12 minutes. And so so the idea is that as circuits will become deeper, stabilizing it over many gate iterations while maintaining fidelity will become more challenging and will require some adaptive scheme. And shot-to-shot fluctuations on longer timescales, of course, will be well within the bandwidth. And this allowing to do this will allow these capabilities will allow us to do increase fidelities of gates in AMO, I believe, given the very a good match between the timescales of gates in AMOs, particularly in ions where gates are typically much slower, and the speed of our FPGA-based system.